Hi, this is Professor Fernandez. In this video, we are going to work on example 2.8 from Calculus 2 Simplified. In this example, we are going to investigate the trapezoidal rule, and we're going to try to use it to develop an approximation to this integral that's accurate to within 0.01. And there's a theorem here that we're going to use, theorem 2.4. I've pasted it in here. I'm going to zoom in here. Feel free to pause the video and take a look at this theorem. We'll go through it in a minute, but it might be good to just read through. There's a lot going on. So, okay, let's take a look at what we would like to do with it. So I have an integral here. I want to use a theorem to determine the smallest n value, guaranteeing that a trapezoidal rule approximation to the integral is accurate to within 0.01. Okay. First thing I'm going to do is read the theorem here. Has a few hypotheses. We will check. Those hypotheses are in here. The conclusion is everything after the then. And since we're using the trapezoidal rule, notice that here there's T sub n is the trapezoidal rule approximation. So we're only going to use actually this inequality when we go off and check the hypotheses. Okay, so first hypothesis here, let f be integrable on AB. So f is the integrand of this integral. So if I look at this integral, 1 over x dx, that's 1 over x here, the f of x. If I draw a little sketch of this function, kind of looks like that between the interval 1 to 2. Those are my limits of integration. So if I look at the area between the graph and the x-axis, it's finite. So that's what it means for a function to be integrable on an interval. So check, right? That requirement is met. This part, let mn and tn be associated trapezoidal rule approximations. Got that. We're working with that one. Suppose one more hypothesis that f is either always concave up or always concave down on AB. Okay, so let's double check that. So I'm going to look at my function, draw this one again, and a couple of ways you could verify that it's concave up. First of all, remember concave up is when the graph looks like a U shape. Right, this is concave up. Concave down is when the graph looks like a hill shape. That's concave down. So we can verify this either by just looking at the graph, which indeed is the case. This graph looks a little U-shaped. Or we can verify this using Calc 1 methods. So if I know that f of x is 1 over x, I write that as x to the minus 1. When I take the derivative, I can use the power rule here. Negative 1 comes down, and then I subtract 1 from the exponent. So this is minus x to the minus 2. I bring this up here and I take another derivative. Power rule again gives me negative times negative 2 because I'm bringing down this minus 2. And then x to the minus 2 minus 1. So this is positive 2 x to the negative 3. This is 2 over x cubed. Now, on the interval that I'm on, over here, 1 to 2, right? Every number between 1 and 2 is for sure positive. So all these x values that I'll be putting in here are positive. 2 divided by x cubed is positive. So f double prime of x is positive. Remember from calculus 1 that that tells me that the function is concave up. So those are a couple of ways to verify this part, that f is definitely concave up in this case for our problem we're working on. Okay, last one, we have found the second derivative. So what does this ask us to do? It says verify that when I take the absolute value of this second derivative, it is at most some number, which we're calling u, on the interval we're interested in. Great, so good thing that we calculated the second derivative over here on the right-hand side. So we have a second derivative of 2 over x cubed. And I would like to know what is the largest that that can be on this interval for x between 1 and 2. Okay, so this way to analyze things that I'm going to describe is useful for other problems as well. Take a look at the actual functional form of the second derivative. Right, in this case, I'm dividing by x cubed. So as x gets bigger and bigger and bigger, if x is bigger than 1, which it is in our case, then x cubed gets larger and larger. Like 2 cubed is 8, 3 cubed is 27. So if I'm taking 2 divided by x cubed, it's getting smaller as x gets bigger. Right? We could also like plot 2 over x cubed. It looks kind of like the graph of 1 over x to see this. So as x gets bigger, the y values get smaller. So the largest value of 2 over x cubed is going to be when x is all the way at actually 1, right? Largest values up here. So we already know that our f double prime x values are positive. Talked about that a minute ago. So our absolute value doesn't change the function. And so we just talked about the fact that 2 over x cubed is largest at x equals 1, and its value is 2. So that tells us that 2 over x cubed is less than or equal to 2. And this is the u value that we are looking for here on the left, right? This is the u value that we need. Okay, so we have all the information that we need at this point. We verified all the hypotheses of the theorem. We have the u value. We know what a and b is. So now let's go ahead and use the appropriate inequality here. So this inequality tells us the error in approximating this integral up here with a trapezoidal rule is at most the u value we found, 2, b minus a cubed. So b is the upper limit of integration, a is the lower limit of integration, so b minus a, divided by 12n squared. And then we can simplify that, right? This is 2, 2 minus 1 is 1, 1 cubed is 1, so the numerator is just 2 divided by 12n squared. Simplify that further, divide both top and bottom by 2, and I get 6n squared. Okay, a couple of things to notice here. First of all, this thing depends on n. And that's why the question says find the smallest n value guaranteeing ... So that's okay. Second thing to notice, we want an approximation accurate to within 0.01. What we have just shown is that the maximum error in the trapezoidal rule is this. So if we can ensure that this quantity we found, 1 over 6n squared, is less than or equal to the error tolerance we want, then we see now that we can solve for n here to tell us what that n value will be. So now we're off to solving this inequality. First thing I'll mention is that the number here is, this is a tenths, this is the hundredths place, right? So 0.01 is 1 over 100. So now I'm solving 1 over 6n squared less than or equal to 1 over 100. I can take reciprocals here to turn this into 6n squared. It flips the inequality sign, greater than or equal to 100. And then now I'm going to just solve this new inequality. The fractions are gone, so life is a little simpler. So here I just divide by 6, n squared bigger than or equal to 100 over 6, and then take a square root of 100 over 6. This isn't exactly a nice number. It's a decimal. It's about 4.08, and then other stuff here. So as long as n, the number of trapezoids you're going to use to approximate your integral, as long as n is at least about 4.08, right? Then your trapezoidal rule approximation to this integral is guaranteed to be accurate to within 0.01. So what would an actual answer look like? Well, n is supposed to be a number of trapezoids. You can't have like 4.08 trapezoids, right? So at least 4.08 means that n equals 5 or larger is the answer we're looking for. Okay, see you next time.